Okay, so hello everybody. I'm Richard Southwell, and this is the third part of this series of talks about the basics of topology. It's really just picking a few fun topics to talk about. So today I want to talk some more about Mobius strips. So let me just remind you what a Mobius strip is. They're very easy to make, which is good. So you take a thin piece of paper and you give it half a twist, and then you join it to itself. So you get something like this. Okay, so you might think that the Mobius strip is just a kind of curiosity, especially since it was only really discovered in 1858. So it wasn't really discovered very long ago. So you might imagine that, unlike the sphere, which is obviously a really important mathematical object, you might think that the Mobius strip is not really that important. But the truth is actually that the Mobius strip is actually very important in what it represents. And so I'm going to talk about a few different ways to think about Mobius strips today. And I'm really going to borrow some ideas from this book here, Experiments in Topology, because this is an excellent book. So one of the questions he poses in that book is, what is the shortest Mobius strip? So for a piece of paper with a given width, how short can you make the length and still have a Mobius strip? So this is a kind of interesting question in a way. For example, try and make a Mobius strip using this piece of paper. Well, you have to give it half a twist and then stick the ends. Well, you can see that it's not going to be possible with paper. I mean, I know we're supposed to be talking about rubber sheet geometry, but let's just think about paper for today. So you can see that this is too wide, essentially, to become a Mobius strip. So we can take some scissors and we can cut away a bit. And now let's try this bit. Can we make a Mobius strip out of this? Well, yes, it seems like we just about can, but it's a very funny looking Mobius strip. It's kind of crushed up. So, in this book they give an example of a construction of a very short Mobius strip. And it looks quite different to the ordinary kinds of Mobius strips that you see. Usually you see these kind of things where it's all kind of continuously curving, but the thing that they describe looks a lot more kind of triangular. So I'm going to show you this here. Let's just get closer to the camera. So here's my basic diagram about how to make this thing. So these blue bits here, these are going to be the outer edge, and we're going to end up identifying A with A prime and B with B prime. And if you look carefully, you can also see these different kind of fold lines where we're actually going to fold the thing up. So let's go. Let's make this into our Mobius strip. So firstly we're going to fold along this first line here. So that would be like that. And then we're going to fold along this second fold line like this, like so. And then I think it's fairly obvious what the last stage of the process is. We just fold this across here. And you can see that A is indeed attached to A prime, and if you open this thing up, You can see that B is attached to B prime, and you know, all is well. You can't actually see all the details inside here so easily. What you'd really want is a kind of transparent surface so that you could see all inside and know everything that was going on. But essentially, if we just get a bit of blue tack here and stick these two pieces together, we have our new kind of Mobius strip. It looks a bit different. Now, I was messing around with this idea last night, and I came across a very similar idea, but I think it's kind of cooler, and it looks weirder, and it looks more complicated, and it kind of looks like some really crazy shape. So I'm going to show you this. It's basically pretty much the same idea. The proportions between the length and the width are the same, and these kind of fold lines are going to take the same sort of angles. What's different though is the way we're actually going to fold the thing. So we'll start by folding, so here we are. These are the different ways we're going to fold it. Okay? So we start by folding one across, and then we'll fold two across. Okay, so start by folding one across, then we'll fold two across, and now you see three is here, so we're going to fold three across. So now what's going on? This is a bit weird, isn't it? Because we've got this edge here, which doesn't have a blue streak on it, so it's clearly supposed to be identified with something. What is it supposed to be identified with? It's supposed to be identified with this thing underneath. Do you see? So what we actually want to do now is identify this with this. So how are we going to do it? We're going to use some scissors. You see, when you're thinking about surfaces generally, you don't actually have to worry that much about self-intersection, or people don't tend to. I mean, you can imagine this was in 4 dimensions or whatever. We're only really thinking about the surface, so the way it looks in 3D space, and if it looks like a piece goes through another piece, that's often not really important to us. So we're going to make this surface self-intersect. So what we're essentially doing here now is cutting a kind of way for this top sheet to go through and touch the bottom sheets. Okay, so hopefully you can see now that we can get this piece here, because let's rephrase what we're trying to do here. We've got this thing here on top, and if we move this away, we've got this thing here, and we want to touch this with this. So the way we can do it now is we can push this through this new hole that we've made, and we can attach it like so. Well, here's one I made earlier. So you can see it's a kind of interesting shape. Okay, so what I'm going to do now is to show you how to walk all the way around this Mobius strip. Okay, so I've kind of labelled a track that you can walk on. So if you start here on 1, you can walk along here and walk along here, and then when you get to the end of here, if you stay on the track, you can go up here up to the top of here, you see? Okay, so here's where it might get a little bit confusing, but essentially you're walking up here and it's difficult to see what's going on because there's this piece of tape here. But essentially, if you follow it properly, you end up walking up here, and then you can come back down again on this part here, which is labelled 4. So you walk back down here. So anyway, we come down this this edge labelled 4 here, and then when we get down to the bottom, we sort of change direction and start heading down here. And so if we just turn it around a little bit, you can see that what we're walking along here is this part here. And in fact, kind of interestingly, if we just flip this over, you can see that it's actually the back of where we started. So just like on the regular Mobius strip, if you walk around halfway, you end up on the opposite side to where you started. So anyway, we continue this journey along edge number 5. So around here, under this, whatever it is, and then when we get to the end here, we just loop around the back and go up here. So you should notice that we're always now on the opposite side to where we were during our last sort of walk around here. So anyway, we go up here and then we kind of jump over the top of this triangle peak, and the path continues down here. This is number 8 now, and you can see that number 8 just wraps round and quite conveniently goes straight back into number 1 where our journey began. Right there. You see that? Number 8 goes round here, and if you actually follow the path properly, it goes back to number 1. Okay, so I want to say something else about non-orientability, because frequently I talk about sides and I say, well, if a guy can get from one side onto the opposite side, that means the surface is non-orientable. So firstly I should say that it's kind of wrong to talk about sides when you're talking topologically about surfaces, because when we think about surfaces, what we really should imagine is that the surface is infinitely thin and transparent. And when we imagine that there's some little creature, some two-dimensional creature walking around inside the surface, or more mathematically, when we imagine that there's some point moving in the surface, we can essentially think of that as a point which is trapped between two transparent sheets. So this point is neither on the top or the bottom of the surface. The top side of the surface and the bottom side of the surface are meaningless terms, in fact. All that matters is that this is a point inside the surface. And now I can explain to you why we say that the Mobius strip is a non-orientable surface. Well, imagine that there was some kind of hurricane on this two-dimensional world, which just happens to be a Mobius strip. So hurricanes spin round and round. Let's say that this hurricane was spinning in this direction, and it moves around the Mobius strip. But remember, it's actually inside the Mobius strip. This is like a transparent Mobius strip, and it's kind of trapped between two transparent sheets. So it started off here where the join is, and it's spinning around and moving as it goes, and it carries on going, spinning as it goes. So then at a point, this hurricane is going to be exactly here. It's going to be on the back of where it started. And so if we now look at the hurricane here, we're going to see it as spinning around in the opposite direction to the way it was spinning before. So if we have a look now through this transparent sheet of paper, we're going to see that this hurricane was spinning the opposite way around to the way it was before. And so that that's kind of why we say that the surface is non-orientable, because it's impossible to associate a particular orientation on the surface, because that orientation can change depending on how you travel. I mean, on a sphere, if you have a hurricane spinning this way, and it's always spinning this way, then however the hurricane moves, you can always see that it's spinning in the same way. But on a surface like the Mobius strip, that's not the case, and it no longer makes sense to think of orientability or the direction that something is turning in as a kind of fixed property, because it can change with movement. Okay, so now I want to show you another non-orientable surface, which I saw in this book called Experiments in Topology. So it's a very easy thing to make this time. The idea is you just get a disc and you cut a radius with some scissors, and then you've got these two kind of flappy bits, right? So you fold one of these flaps over like that, so it kind of touches the centre, and you do just the same thing with the other flap, but you fold it on the bottom, so it touches the centre on the bottom. And then you just stick these flaps in place. I shall use a bit of glue tack. And now, strange as it may seem, we actually have a kind of non-orientable surface here. What I mean is that if we kind of puff this out a bit, make this a bit more circular, a bit more tubular, then you can see how it's a non-orientable surface. So here's another construction of this non-orientable surface that I made earlier. It's a little bit more robust. I made it larger and I used some tape. So I shall just show you quickly how this is non-orientable. So a small two-dimensional creature could start here, and they could sort of walk through this hole here. And what would happen to them? Well, they'd obviously go through this hole, go through here, and then they'd come out on the other side. So now we can turn this around. So I've labelled this side top, and they can come out on the top, and then if they want, they can kind of jump over here. They can jump over here, and they can get back to where they started. So the important thing is that a little two-dimensional creature can get onto the opposite side of the paper as to where they were before.